Swayam Prabha. Digital India. Educated India.
We continue our discussion of quantum harmonic oscillators today. What we will do in this module is that we will talk about the energies of harmonic oscillator, and we will talk about actually one wave function. We will perform a more detailed discussion of the wave functions and how they are interrelated in the next module. Today we will talk about the lowest energy wave function. Let me start with a spoiler. What you see here, well, we have seen this in the last module as well, is the potential energy surface of a quantum harmonic oscillator, in which we have shown the different energy levels that are allowed. Remember, energy is quantized here, and quantization arises out of the boundary condition that the wave functions must become 0 at x equal to plus infinity and minus infinity. And as you can see, the wave functions do not exactly terminate at the potential energy surface. They go a little bit beyond, and it was your homework to find out why this is the case, how this is justified. Please read about this and post on the forum. But if you look at the wave functions, they look somewhat similar to the particle in a box wave functions. The lowest one is pretty much a Gaussian function without any node. There is one node in the second one, 2 in the third one, and as you go higher up, number of nodes in the wave function increases. As a rule of thumb, energy and number of nodes go hand in hand. A more energetic wave function would have a greater number of nodes. This is perhaps something that you have studied axiomatically at in high school as well. Today let us go ahead and see how one can arrive at the expression of the energies and at least one of the wave functions. But before that, let us do a brief recap of what we have studied in the last couple of modules. We have said that harmonic oscillators are those which obey Hooke's law. So, in the classical domain, solution for x, the displacement from mean position, would be a sin omega t plus b cos omega t, where omega is the angular frequency of oscillation. Please note the term angular frequency of oscillation. By the time we close the discussion in this module, we will have something to say about that. So, this angular frequency of oscillation is popular because it is simply root over k by m, where k is the force constant of the spring and m is the mass. So, for a harmonic oscillator, from classical mechanics itself, we know that the potential energy is parabolic. So, what we do is we take this parabolic potential and we plug it into the Schrodinger equation in place of V. So, the first term remains the same, the kinetic energy term. The potential energy terms becomes half m omega square x square psi equal to E psi. As we have said earlier, the beauty of Schrodinger treatment of quantum mechanics is that you start with classical quantities, and then when you try to interpret the wave functions, the unique features of the quantum world manifest themselves automatically. That is what will happen here as well. So, this is your Schrodinger equation, and we said that there are two ways of solving it. First is the power series method, which we will come to later on, and what we are doing right now is the algebraic method, and the most important thing about the algebraic method is the ladder operators, to which we have been introduced in the last module. So, the way we got to the ladder operators is that we wrote Schrodinger equation, and remembering the operator for linear momentum h cross by I ddx, we plugged it in and we wrote the kinetic energy term as p square psi by 2m. Remember, we are not writing the hat here, but p is really an operator, the momentum operator, it is not a number. second term. Since there is a 1 by 2 m here, we take 1 by 2 m common from the second term as well. So, that you get square of m omega x operating on psi. So, the Schrodinger equation becomes like this, 1 by 2 m, then p square plus square of m omega x, the whole operator, this is the Hamiltonian, this Hamiltonian operates on psi to give you E psi. So, what we have done essentially is that we have rewritten the Hamiltonian in terms of the linear momentum operator. And then what we said is that this Hamiltonian here is sort of u square plus v square kind of term. So, if it was a number, you could have written it as iu plus v whole thing multiplied by minus iu plus v. But then since these are operators, that will not be the case, but let us see what happens when we take this iu plus v, u here is p. So, ip plus v is m omega x, ip plus m omega x and minus ip plus m omega x, iu plus v minus iu plus v. What we said is let us take these two quantities anyway, work out their products and see how far we are from the Hamiltonian. And as we said, this factor that is there, that is because we already know what the solution is going to be. So, solutions look better if we have this 1 by root over 2 h cross m omega, right. A minus and a plus, these two are operators in themselves, these are our ladder operators. And we also asked you to work out that the commutator of a minus a plus is equal to plus 1, which means commutator of a plus a minus is minus 1, right. And since the commutator is not equal to 0, what happens is the Hamiltonian is not just a minus a plus or a plus a minus. What we get is that the Hamiltonian is written as h cross omega multiplied by a plus a minus plus half, or you can write it as h cross omega a minus a plus minus half, right. Both are valid forms, we use the one that is more convenient given the situation we are in. So, this is how you rewrite the Hamiltonian in terms of the ladder operators a plus and a minus. Then we came to this question, why is a plus called a plus, why is a minus called a minus? Because we proved that when a plus operates on psi, it produces a wave function which has an eigenvalue of E plus h cross omega. E is the energy of psi, the original wave function. So, when a plus operates on that wave function, energy of the resultant wave function is increased by h cross omega, which is one vibrational quantum for this harmonic oscillator. Okay. That is why a plus is called a raising operator. It takes us up by one step in the energy ladder of the quantum harmonic oscillator. Similarly, when a minus operates on psi, the eigenvalue that we get for the new wave function a minus psi, again unfortunately I have repeated the error of last module, sorry about that, this will be a minus of course, but the wave function, the eigenvalue is E minus h cross omega a minus psi. This is a minus, please correct it in your notes, a minus. So, this is called a lowering operator. And the good thing about this is that in principle, if we know one wave function, we should be able to work out the others by going up and going down the ladder using the appropriate ladder operator. If we know the energy of one level, we can work out all others, and this is something we will do in the next 15-20 minutes, right. So, this is what we had said, and now with this background, let us try to find out the wave function of the lowest energy state. Of course, the question that should arise here is that is there a lowest energy state or is it a bottomless pit? I mean, can you go down further and further? Can you go down to minus infinity energy? Can you go down to plus infinity on the higher side? Can you do you have to stop at 0? Well, minus infinity and all might be stretching things a little bit. What is the meaning of negative vibrational energy? But then if we think of the classical harmonic oscillator, then we can expect that the lowest energy state should have energy equal to 0. As we touched upon briefly in the module before last, for a classical harmonic oscillator it can come to rest, right. It does not have to vibrate all the time, does not have to oscillate all the time. what happens here. So, to do that we will use a clever trick, and once again I am using the treatment used in Griffith's quantum mechanics book. Let us say psi 0 is the wave function for the state with lowest energy if there is one. Well, there will be one. So, psi 0 is the wave function of the state with lowest energy. See, if I apply A plus on psi 0, what happens? I go up higher up the ladder, yeah, I get the wave function, or I get a function that is proportional to the wave function that has energy which is higher than this lowest energy wave function by one step, one quantum h cross omega. What happens when I apply A minus on this supposedly lowest energy wave function? There is nothing below it. So, when A minus operates on this wave function, let us say what have I called it? I have called it psi 0. When A minus operates on psi 0, will you agree with me that I should get 0? Not because the energy is 0, not because the eigenvalue is 0, but because the resultant wave function itself should be 0 everywhere, or in other words it should not exist. Okay? Because if psi 0 is the lowest energy wave function, you operate A minus on it, where do you go? There is nowhere to go. So, that state does not exist. So, the wave function cannot be there for it. So, that wave function has to be 0 at all values of x. In other words, we can think that probability of finding that state is 0 everywhere. So, psi star probability density is 0 everywhere, therefore, psi also has to be 0 everywhere. Psi has to be 0 everywhere. Okay. So, A minus psi 0 produces a wave function that is 0 everywhere, that is why we write A minus psi 0 equal to 0. I hope you understand this. This is a very crucial step. See, mathematics and all will work out, but it is important to get the logic, and the logic is quite subtle sometimes. If you miss it, then we might not get it in a lifetime. Alright. So, A minus psi 0 equal to 0. Now, we know what A minus is, right. This is A minus 1 by root over 2 h cross m omega multiplied by I p plus m omega x. When this operates on psi 0, I get 0. We know what x operator is just multiplication by the value of the position x. What is p operator? This is p operator, h cross by I d dx. So, what we will do now is that, what are we trying to do? We are somehow trying to find what psi 0 is. To do that, we need to set up some equation in psi 0. So, that becomes easy when we take this expression for the momentum operator h cross by I d dx, plug it into the expression for A minus, and we get 1 by root over 2 h cross m omega multiplied by h cross d dx plus m omega x psi 0 equal to 0. It is a differential equation, right, first order differential equation. First thing I can do is I can get rid of this factor 1 by root over 2 h cross m omega, because that will be equal to that is of course not equal to 0. So, rest of it has to be equal to 0. So, what I get is h cross d psi 0 dx plus m omega x psi 0 equal to 0, right. Simple first order equation. I think most of you would be able to solve it without me doing it, but we will do it anyway. Now, let us rearrange in which I have everything in psi 0 on one side and everything in x on one side. So, this is what I get, h cross d psi 0 by psi 0 is equal to minus m omega x dx. What would the next step be? Pretty obvious. Next step would be to integrate it, yeah, h cross integral d psi 0 by psi 0 is equal to minus m omega integral x dx. Simple. What is d psi 0 by psi 0? Everybody knows, it is ln psi 0. What is integral x dx? It is x square by 2, and let us keep it indefinite for the time being. So, we will get h cross ln psi 0 minus m omega x square by 2 plus some constant of integration, okay, pretty simple. Now, for the sake of convenience, what I will do is I will write the constant in logarithmic form as well, because if I can somehow bring it here inside this log, then I can just take antilog on both sides, raise both sides to the power of e, and I will get a nice expression. So, what I will do is I will write this constant as h cross ln A. Then it becomes simple, you can just take it to the other side, it will become h cross ln psi 0 by A. Then raise both sides to e, we get psi 0 equal to A multiplied by e to the power minus m omega x square by 2 h cross, right, simple. So, we have got psi 0, have not we? We have already found what this lowest energy wave function is. Well, almost, but not quite, because we still have to find out A. And if you remember the properties of wave function, the wave function has to be normalized. So, we can treat A as a normalization constant, and when we consider normalization, what it means is that integral for values of x from minus infinity to plus infinity of psi 0 squared dx has to be equal to 1. So, we write like that A square, ideally I should have written mod A square, but I know in this case we are going to get a real value of A. So, I have been a little lazy and we have written just A, not mod. So, A square is a constant, comes out of the integral sign, integral minus infinity to plus infinity e to the power minus m omega x square by h cross. So, here we had e to the power minus m omega x square by 2 h cross, take square of that, this 2 in the denominator would go, simple. So, e to the power minus m omega x square by h cross integrated for x equal to minus infinity to x equal to plus infinity, that should be equal to 1. Now, this minus infinity to plus infinity integral, this is a standard integral, the value is known, you can look up a compendium of standard integrals and you can find out what the value is. Generally if you are asked to work this out in an exam, the value of this integral has to be given, right. So, we will do that, and believe me when I say that this value is root over pi h cross divided by m omega. So, a square multiplied by root over pi h cross by m omega is equal to 1, rest is simple, square root of m omega by pi h cross is equal to a square. So, a is equal to m omega by pi h cross raised to the power 1 by 4. Of course, you can ask why have I not taken the negative root, I could have, it does not matter. For wave function, actually you have to define one wave function and work with respect to it. So, if you want to write minus, be my guest, but generally wherever possible we keep the positive value, that is the convention. So, A is there. Now, we can say that we have found the wave function psi 0 and it is 1 m omega to the power pi h cross raised to the power 1 by 4 multiplied by e to the power minus m omega by 2 h cross x square. What kind of function is this? Gaussian function. So, if you remember the diagram I had shown you at the beginning of this module, the lowest energy wave function was Gaussian, right. This is it. So, we have been able to work out the wave function of the lowest energy state, right. What is the next step? The next step is to find the energy. Okay. Since you know the wave function, what we will do is we will take that wave function and we will make the Hamiltonian operate on it. So, energy should come as the eigenvalue of this wave function, that will be the lowest energy. So, what we will do is we will use the convenient form, we could have used the differential form also, but since we are using ladder operators and since ladder operators are so convenient, we will use the form of Hamiltonian with the ladder operator. You could have used the other one as well. This is actually more suitable in this case, you will see in a moment why it is so. So, h equal to h cross omega multiplied by a plus a minus plus half. This is the form of Hamiltonian we will use. So, h psi 0 then becomes h cross omega multiplied by a plus a minus psi 0 plus half psi 0, that should be equal to E psi 0, right. Now, one thing to remember from the last slide is that we know very well that a minus psi 0 is equal to 0, right. We started with that consideration, the psi 0 is the lowest energy wave function. So, if you try to lower it, there is nothing to go, nowhere to go. So, the wave function that you will get is actually 0 everywhere. So, this is very convenient, a minus psi 0 is 0. So, even if you apply a plus to that, a plus 0 is also 0. It is 0 everywhere, you do not know what to do with it. So, conveniently the first term becomes 0, only the second term survives. So, what you get then is that second term is half h cross omega multiplied by psi 0. So, Schrodinger equation reduces to h psi 0 equal to h cross omega by 2 psi 0. Okay. What is the eigenvalue here? H cross omega by 2, and that then is E0, the energy of the lowest energy vibration state. Okay. Psi 0 has an energy of half h cross omega. This, if you remember from our introduction, is called 0 point energy. This is the smallest energy a quantum harmonic oscillator can have. It can never be 0, because if it was 0 then it would have violated uncertainty principle. So, even if you take the oscillator down to 0 Kelvin, it will oscillate with the frequency of half h cross omega. This psi 0 will be the only state that will be occupied at that case. In fact, for most of the molecular harmonic oscillators, this is the only state that is occupied in room temperature anyway. To know further, please look up our NPTEL course on molecular spectroscopy. But let us proceed from here. E0 is half h cross omega, great. Now what can we do? If you remember, if we use the step up operator, a plus ladder operator on psi, then in Schrodinger equation the wave function becomes E plus h cross omega. Okay. So, what I am saying is this, you just keep on applying a plus. Let us apply a plus to psi 0. What will I get? I should get psi 1, the wave function that has energy that is just one step above that of psi 0. So, that E1 will be equal to E0, energy of psi 0, that is half h cross omega plus h cross omega from here. What will E2 be? E2 will be, well sorry, so E1 will be, then I can take, I can write this E0 as half h cross omega, and I can take h cross omega common outside the bracket. So, I will get 1 plus half h cross omega, 3 by 2 h cross omega, but let me write it in terms in the form 1 plus half, because that will lead us to the general form of the energy anyway. So, E2, what will E2 be? I can again get E2 by making a plus operating on psi 1, then it should be E1 plus h cross omega. E2 should be E1 plus h cross omega. What is E1? E1 is 1 plus half h cross omega. Add 1 to that, what do you get? Simply you get 2 plus half whole thing multiplied by h cross omega, and so on and so forth. So, what we have seen is that even though we have not really worked out the wave functions for the higher energy states, we have been able to work out the energies. So, what happens for EV? EV would be EV minus 1 plus h cross omega, that would be V plus half h cross omega. What is V here? What is the range of V? V ranges from 0 and it increases by an integer each time, 0, 1, 2, 3, 4, right. So, this is the vibrational quantum number, and what we see here is the most general form of the energy of a quantum harmonic oscillator, EV equal to V plus half multiplied by h cross omega, where V equal to 0, 1, 2, 3 etc., can go up to infinity. These are the vibrational quantum numbers. Okay. So, what we have been able to do is we have been able to find out the expression of energy of not only the lowest energy state, but all energy states of the quantum harmonic oscillators simply by using ladder function. So, EV equal to V plus half h cross omega and V equal to 0, 1, 2 etc., right. Now, before going further, I would like to say one thing. Since I am a spectroscopist, I like to rewrite this equation somewhat. Remember, omega is angular frequency. A spectroscopist usually likes frequency better than angular frequency, no particular reason, just convention. So, what I can do is I can write h cross as h by 2 pi and omega is 2 pi multiplied by nu, right. Omega is angular frequency radian per second and nu is frequency per second. right. So, these are dimensionally consistent. So, this 2 pi and that 2 pi will cancel and you will be left with h nu. So, what I could do is, what I like to do is, I like to write EV equal to V plus half into h nu. What is h nu? 1 quantum of vibration. Okay. And I like this because when there is a transition from one state to the other, what you are left with is h nu, and this frequency of vibration turns out to be the frequency of light that it absorbs as well if it undergoes a V to V plus 1 transition. And as it happens, for simple harmonic oscillators, quantum harmonic oscillators, only V to V plus 1 transitions are allowed. There is something called selection rule. Just because you have energy levels in a system does not mean that one can absorb, it can absorb light and go from any energy level to another. Only certain transitions are allowed, others are disallowed. One selection rule that I think most of us are familiar with is Laporte selection rule. Remember, DD transitions are not allowed, right. So, similarly in quantum harmonic oscillators only V to V plus 1 transitions are allowed, others are not. For such transitions the energy difference simply turns out to be h nu, where nu is the frequency of vibration of the oscillator, and then that will equal to h nu, where nu is the frequency of light also. So, interestingly, a quantum harmonic oscillator absorbs light whose frequency matches its own vibrational frequency. We have dealt with this a little in a little more detail in the molecular spectroscopy course. Okay. So, this is our expression where we wanted to get EV equal to V plus half h nu. We know the expression for the energy of all the vibration energy levels of the quantum harmonic oscillator. But until now we know only one wave function, psi 0 equal to m omega to the power pi h cross raised to the power 1 by 4 multiplied by e to the power minus m omega by 2 h cross x square. What should the next goal be? The next goal obviously should be to find psi 1, psi 2, psi 3, psi 4. Okay. How can we do it? We can do it by using ladder operator, but then we will also use this analytic technique which will allow us to arrive at some very beautiful relationship among the wave functions in a vibrational manifold, and in fact that is what leads to the selection rule. So, what we will do in the next module is that we will try and understand how to find out the expressions for psi v, the wave functions for the vibrational levels other than v equal to 0. V equal to 0 you already know. So, that will require maybe 2 modules after this. Today for this module we close our discussion.